That's extra credit.
Okay. So I have the homework tools for those who have not picked them up yet. So I just distribute them at the end of the class outside, so that you don't have to walk out of there. Also, Sushant told me that the project part 1 has been graded, but he hasn't yet entered the grades. So that's why I couldn't bring it today. So it should be available. I'll bring it to the class next class, but it probably will be available earlier than that if you need to see it. So that's regarding all the homeworks and grading. Any questions? No questions? What? Not too many in the exam, but that was the ones I asked, not you asked. Okay, so we are continuing the discussion of the topic that we were doing before the exam, which was clustering. And so we were looking at clustering example, this particular one, for example. So you started with some initial seeds. Normally, you can pick any two. If you know K, then you pick K seeds. And I guess a reasonable heuristic would be to pick seeds far away from each other. But in general, it's not obvious as to what are the best seeds. We'll see that in a minute. And so, in this particular case, I'm just going to fast forward through this. So you started with a red seed and a blue seed, and I was looking for K equal to 2. And so then everybody decides the distance to the centroid of the existing clusters. And then whichever distance is lower, they will just shift over to that. That's basically what they'll do. And that's what happened in this case. Now you have a red cluster and a blue cluster. And then, so you have a centroid for the blue cluster now is here, then centroid for the red cluster is here. Right? Yes, there was a question.
Actually, I just wanted to know the local minima and the global minima. Actually, I was just confused about that.
So, I mean, no, in general, so basically if you go back, what K-means is trying to minimize is the, let me go through this, I'll get to that, okay. So, you have the centroids for the red here and the blue there. Centroids for the red here, the blue there. At this point, then everybody again, in the next iteration, everybody synchronously decides to switch, decides again which cluster they belong, okay. And the way they decide which cluster they belong is by looking at their distance to the centroid. In these cases, when I'm saying distance, any distance would be fine, but for text, normally you would use cosine theta distance. Okay, similarity, which is distance, inverse of it. Okay, so in this case, I mean, of course, in the picture itself, we are sort of thinking in terms of Euclidean distance. You are actually, I'm expecting you to think in terms of Euclidean distance because that's why you can see which one is closer, which one is farther apart. Okay. Clusters might be different if you use a different distance metric. Yes. Okay, so in this case, then the next iteration, basically, these red guys will realize that they are closer to this one than to this one, and so they shift. Okay, and so now you have now you can recompute the centroids again. At this time, the blue centroid goes there. Again, you just think in terms of the Euclidean distance, you can see that. And then red one is here. At this point, nobody is shifting. Nobody is shifting any further. Okay, because none of the points have, none of the points is the centroid to a different cluster any closer than the centroid to the cluster they are part of. So they stay there. Okay. At this point, you no longer, I mean, the iterations have stopped. and so you reach some sort of a minimum. Okay. Now, so in this case it's converged. So the question, of course, is exactly what is being minimized, and we talked about this last time, and repeating it again. If you consider the tightness of the cluster, okay, so if I have multiple clusters, okay, in each of them there is a centroid, okay, so you take each point in the cluster and the distance of that point to the centroid, sum those distances, in this case actually sum of squares of those distances, okay, so you would get the, so a number here, a number here, a number there, you add them all up, that would be in essence, if this cluster is very tight, that means everybody is close to the centroid, this sum would be close to 0. And similarly, if this cluster is also tight, it will be close to 0. If this cluster is also tight, it will be close to 0. So the sum of all zeros would be 0. So if they were not tight clusters, then the sums would be larger. Okay, so you would consider, remember however that we talked about the fact that clustering actually, the quality of clustering is really a function of two things. A function of intra-cluster tightness and inter-cluster distance. Okay, so the point of clustering is to make each cluster be tight and be far away from the other clusters, intuitively. So you have to have a function, a quality measure on the clustering has to be taking both into account. In the case of K-means, you'll only essentially consider the intra-cluster tightness. Okay? Why? Because in essence the K is constant. So if everybody becomes tight, then they're also becoming far from the clusters, far from the other clusters. Okay? So for the same given K, this you can ignore the inter-cluster distance and you just consider the sum of the cluster tightness. Okay? And if this measure, if you consider this measure, as you go from iteration to iteration to iteration, notice that in each iteration, somebody changes the cluster if they find that they're actually closer to the other centroid than to this. That means, so suppose, we had a funny looking cluster like this, let's say, where a point was here and it was being, it was contributing to the dissimilarity of this cluster. Because here is a far away outlier in this cluster and it was taking this much distance and you're squaring it and adding it to the tightness of the cluster. So this cluster is pretty bad. Okay, now when this guy shifts over to this, suddenly, make it even better actually. Something like that. Okay, when this guy actually shifts over, then this cluster becomes like this and this cluster becomes like this. Now everybody is happy because this guy now no longer has to deal with this amount of distance and this guy is taking an extra distance, but then that's not as bad as this guy is not happy. His tightness has actually increased, his dissimilarity has increased. Except the overall sum hasn't increased. Overall sum actually has reduced. Okay? So in general what happens is K-means clustering, each iteration, this measure keeps reducing. That's what we were talking about last time. And when you reach a minimum and you're no longer able to change between two iterations, then you have reached a particular value and you're unable to change any further. That, however, does not mean that that is actually the best possible. Why? Because it turns out that the place you start the K-means, the seeds that you start with, will have an effect on what clusters you will find. Okay, we'll see an example. I think I mentioned it last time, but we'll again see it. So the actual seeds you start with does have an effect on the clusters you end up with. Okay, and if you want to stick to any initial seeds, then you have to consider allowing multiple nodes to move in tandem. Multiple nodes to move in tandem. And if that is allowed, again, you can get global optimum. Okay, those are not allowed, so we are considering one node at a time. Each element makes an independent decision in this case. Each data point is making an independent decision as to which cluster to go to. Yes?
I have a stupid question. In the previous slides, it converged, but if it doesn't converge, then we want two clusters with data.
You will always converge. K-means will always converge because there will always be some lowest value it will reach. All we are saying is it may not reach the globally lowest value. Okay? So anyway, so the reassignment monotonically decreases this thing, except so it reaches a local minimum. So in some sense, this is the point about function minimization, right? Suppose you have, in your two-dimensional functions that you have done in calculus, right? You can look for a minimum or a maximum of a function by looking for the places where the slope is 0, the derivative is 0. Derivative is 0 doesn't necessarily tell you that it is global maximum. It only tells you that it's a local maximum. Okay? And in general, any iterative technique could get stuck in a local maximum or local minimum. That's the difference. Okay? Whereas if you consider looking at multiple different initial seeds and look at K-means on each of them and see the best clustering you will get after all of these, then you can get something closer to the global outcome. Okay? Yes. There's a question? Yeah.
So we're done with these by randomization, right?
You could do that by randomization. I mean, there are multiple. I mean, this is a central problem in optimization in general. Okay, because you want to find, especially in continuous optimization, like function, finding the optimum of a function, you can't do exhaustive search. You sort of need to go, iteratively, sort of hill climbing local search techniques. And they'll always get stuck in the local minimum. So the only question is, what are the ways in which you can make your hill climbing be slightly better? And there is a whole bunch of techniques. But that is different. I mean, so the only point you want to understand here is, that student was asking, what's the whole local minimum, global minimum issue? This is the point. So you might get stuck in the local minimum instance. Okay. So this is basically what I just said. And okay, and here is one more example just in case you are, so actually these examples here, you're showing it graphically, right? I mean, so you will actually, for each of these points, you can compute the Euclidean distance between the point and the centroid, and then decide which cluster to go to, okay? And I just have another example here. You can follow this next, after the class. Here, this is one-dimensional objects, okay? And I'm looking for two clusters, okay? K-means with two clusters. It's one-dimensional object. So each object this is object of 1, 2, 3, 1, 2, 5, 6, and 7. Imagine that the distance, of course, is just the difference between the absolute difference between those two numbers. Okay. So then, suppose I were to pick 5 and 6 as the centroids. This is just one more example. Okay. Then I would. So then 1 and 2 will go into the cluster with 5, and 7 will go into the cluster with 6. Not surprising. Okay. So then your two clusters will be 1, 2, and 5, and 6 and 7. At this point, the cluster center for this will be 6.5, and the cluster center for this would be 8 by 3. Okay. Now everybody gets to again check which one are they closer to. Are they closer to 8 by 3 or 6.5 in terms of one-dimensional absolute distance? And then shift over to the cluster they're close to. In this case, you get 1, 2, and 5, 6, 7. At this point, again, you can compute the centroids 1, 3, 5, and 6. At this point, none of them change, so K-means again stopped here. So it's yet another example. This is a one-dimensional example. Okay. And what's interesting is that for this case, you can actually compute the aggregate dissimilarity, which is each cluster's dissimilarity. Okay. So for example, this one. So it's when you stop. I'm just computing where I stop. When I stop, this is 1 and the center is 1.5. 1 minus 1.5, 0.5, so 0.5 squared. And 2 minus 1.5, 0.5, so 0.5 squared. And then here, 6 is the middle, so 1 square plus 0 square plus 1 square. So the aggregate dissimilarity for this case would be 0.5 square plus 0.5 square plus 1 plus 1, 2.5. Okay? And if you were to compute this aggregate similarity for the earlier, the first one, that would be higher. This is lower. Okay? So that's how that metric is coming down every iteration. So that's the optimization metric. Yes?
So there can be a point which can tie both of the clusters.
That point, it doesn't change, right? Basically, so breaking ties, if you are equally close to, two clusters, then you just pick one. Although, indecision, how many of you know of the Buridan's donkey? So this is a famous allegory of a donkey which was equidistant from two piles of hay and couldn't quite figure out which one to eat from and died. Starved to death. Right? So when you are equally distant, when you are from equal distance, then you just break the tie. Of course, some of us, this is a different point altogether, but we do sometimes spend large parts of our life trying to make decisions between two alternatives which are nickel difference, okay, which are equal more or less. We waste our lifetime essentially trying to figure this, which one should I do? Should I do this? Okay. So anyway, but in this case, K-means is not Buridan's donkey. Okay, so it would pick any of them when they are both close. That's what is the rational thing to do. Yes.
Can we not check the sum of squares for both the cases and see what is better in that one?
What are you talking about?
You're talking about picking one of the choosing which cluster.
It won't be different, right? It cannot be different. Because again, the structure is such that if in fact a particular point could have is this distance is equally distant from this and this, then whichever you put it in, it adds to the final sum the same distance square.
But the centroid can change, right?
What?
The centroid can
No, remember, this is again, we are talking about synchronously. In the synchronous, so you're talking about after everything is over. That would be making K-means much harder. Then you might as well consider doing K-means with multiple initial starting points. See, it's not that you can't make this optimum, it's just that anything more than K-means tends to be less efficient. That's the point. So it's not, so you are essentially saying, for each decision point I had, go all the way down and then see if in fact I could have done better if I had done the decision differently. Then why you only do that for the decision where you are equidistant? Why not do it for everything? In fact, even when you are kind of close to this centroid, maybe you shouldn't go to this centroid. Maybe after you move, lots of other people will get to this, lots of your friends will get to this, and so you really should have moved here. The efficiency of this is you are making independent decisions. Okay? Okay, so we talked about this, and so now K-means problems. Okay, this is K-means. It's a very classical algorithm. Some of you probably heard about this already. And so let's talk about some problems with this. One is, of course, you need to know K in advance. In some cases, you know how many clusters are to be found. If you tell K-means to find K clusters, it will find K clusters. Exactly K, no more, no less. Okay, as long as K is less than N. If it's more than N, obviously, then it can't find K clusters. Okay, now, one problem, of course, is we don't know the number of clusters, and so since you don't know exactly how many clusters should you ask K-means to find. Okay, one idea could then be to say, why don't I just do K-means cluster with K equal to 2, K equal to 3, K equal to 4, K equal to 5, and see for each of them find what clustering you get, take the intra-cluster dissimilarity sum, and pick that. Pick the clustering. So for example, for K equal to 2, you got, eventually in the end, you got 2 clusters, and their dissimilarity is, let's say, 7.5. And then K equal to 3, you got yet another clustering whose dissimilarity is 7.0. And another K equal to 4, you got another clustering whose dissimilarity is 6.0. So then you will pick the one for 6.0. Right? What's wrong with that?
You will get down to 1.
You will get down. So the problem is because we are not considering, we are only considering the cluster tightness, there is a way of defeating this algorithm. If you have n equal to k, when k equal to n, then everybody is in their own cluster and they are very tight, and so the cluster dissimilarity would be 0. So eventually you'll fall all the way to 0. So in some sense, as you increase the number of clusters you are trying to find, you will, by definition, reduce the cluster dissimilarity measure. Do you understand what I'm saying? So another way of saying it is the way I can make sure that, remember with grading is a clustering, an exercise in clustering. Okay, the way I can make sure that I'm not putting anybody in the wrong grade is to leave that there be 52 grades. If there are 52 people, okay, and whatever is your cumulative, score up to 7th decimal point, that is your grade. And that way you will not be put with anybody who is smarter than you or less smart than you. And none of you can complain. Okay, but obviously there your clusters of size 1. Okay, so by increasing the cluster, number of clusters, you can only reduce the type, dissimilarity. And yet it is the case that given an example, like for example, given this real data, okay, I can sort of see 3 clusters. Okay, I can sort of see 2 clusters, I can sort of see 3 clusters. I don't see 9 clusters, for example. Okay, so there seems to be a natural number of clusters here. How do I catch that? And the answer to that is, if you are trying to guess k, then you can't just keep increasing k. You essentially have to look at the rate of change of the dissimilarity measure as k is being changed. And you need to look for the mean in that curve. Okay, in particular, suppose, this is for some problem, I am compute this on y-axis I have the dissimilarity measure, on the x-axis it's clusters k equal to 2, 4, 6, 8, 10. Clearly it will keep falling eventually, right? As you increase the number of clusters, it will keep falling, the dissimilarity measure will keep falling. But if you look at this curve, you can see that there are 2 natural points where you should start. Right? Because there is a inflection here, there's a knee here, and there's a knee here. So either go with 4 or 6. That would be the natural number of clusters in the data. Do you see what I'm saying? Okay? That's obviously costly to do this. Okay? But that's what you will need to do if you really are trying to find what is the right number of, what's the right k to look for. Okay? One idea that you could do is, suppose you're trying to find the k-means clustering on a trillion text documents. Okay? Obviously, reclustering them for once for 2, 4, 6, 8, 10, etc. is going to be too costly. So instead of clustering the entire trillion documents, you can randomly sample a small set of the documents from the trillion documents. And if it's a uniform random sample, that means, basically it's not a bias sampling. Suppose I just get like instead of trillion, I get like 10,000 documents. And for those 10,000 documents, I assume that they have the same aggregate properties as the trillion documents. And then I can do this for the pre-processing stage, and figure out what k I'm looking for. And then take that k and give that as the input to the k-means clustering on the trillion documents. That's the way you can find k. Okay? A different way of doing it is to actually write this as an optimization problem, where the optimization measure is not just dependent on the intra-cluster dissimilarity, but also is dependent on somehow the number of clusters. And you need to kind of provide a penalty, a regularization term, for those of you who have background in machine learning, which says that the the number of clusters increase, you get penalty. Okay, and so the total objective is the intra-cluster tightness minus the number of clusters you have, R plus probably in this case. So the number of clusters have to increase the value essentially, since we are looking for the lowest. As the number of clusters increase, the objective function has to increase. Okay, so that means the same dissimilarity, 3.5, is going to be better objective when the clusters are 2 and worse objective when the clusters are 7. And if you do that, and if you do like an exhaustive search, iterative search in that, with respect to that objective, then you can get K-means, where you sort of find the right K. Okay, that's a more costlier approach. I'm not going to discuss this, but there are approaches like that. Yes, there was a question. Yeah. Yes.
Why inter-cluster distance is not included?
What?
Inter-cluster distance.
Well, this, in some sense, number of clusters will catch that. For example, you can do it. No, you don't need to do the. If you keep the K same, then the inter-cluster distances doesn't have to be included. If you can change the K, then you do need to consider the inter-cluster distance. And in this particular case, the number of clusters sort of stands in for that component. But there are many other ways of defining this. I'm just saying that K-means is very cheap, but it also has its problems, and such as it requires the input of K. And if you have to figure out what's the K, you can either do it by doing a pre-processing on a subpart of the data, or you do it on the trillion documents, except you do a different optimization. It's not going to be like K-means anymore. Okay? Fine. The other thing, of course, as I said, is K-means tends to go to local minima that are sensitive to the starting seeds. Okay? As an example, starting seeds. As an example, suppose I have this as my data. Again, imagine Euclidean distances. And if I start with B and E, I would get A, B, C, and D, E, F as the final clusters. Whereas if I start with D and F, I will start with A, B, D, E, and C, F as the final clusters. Now in this case, you could have said, well, B and E are not as good as D and F because D and F are already far apart. And so it's always a good heuristic to start with things which are far apart. But in general, that's not a fail-proof idea. It's a heuristic. Okay. So in general, you have this problem that if you have, the optimum you get to is sensitive. So even if you know what the right K is, then the optimum you get to is still sensitive to the starting points. Okay. So the answer to that, how do you deal with that problem? The answer to that is essentially to actually start, try multiple different, one heuristic, of course, is look for initials and draw initial seeds that are far enough apart. Okay. Another is try running K-means like 7 times with 7 sets of seeds and see which clusterings they come up with and pick the clustering that's the best. And since K is constant across all these 7 runs, you are comparing apples to apples. Okay? So that's the way you deal with that. In fact, we'll see that, we'll see an approach in doing this. In fact, we'll see in a minute an idea called bisecting K-means, which sort of answers both these questions in an interesting way. Okay. Then there are other problems which we would not particularly go into here, but for example, K-means is disjoint and exhaustive. Okay, disjoint in the sense every point should be in a single cluster. It cannot be more than one cluster. It can't have partial membership in clusters. Okay. Exhaustive in the sense every point has to belong to a cluster. That's the outlier problem. Okay. And again, going back to the grading analogy, I haven't yet completed my grading, but suppose it so happened that one of you got 65 and the next highest was, 40, okay, and then it was 40 and below, okay. Then if I'm trying to decide gradings, all of you would say remove the 65% because they are not reasonable people. You know, they should be in the clustering for the grades. They're outlier. They probably had the exam paper before, okay, something or other. So you would argue for an outlier. So let's not even use that person, you know, in the clustering, okay. And that's, how do you figure out that something is an outlier? Removing outliers and doing clustering will help because outliers do change the final clusters you come up with. In fact, I'll show you one particular here. I think it so worked out that I already completed the grading and I had the raw numbers for midterm available. And so I used that actually as the example for showing this. And I will send you that example. And there was an outlier. I mean, there's always an outlier in classes. I just don't show them to you because I'll have one person less then. So the point being that when you have outliers and if you keep them, the A, B, C cutoffs will be completely different from if you don't keep them. Okay? And to the extent the outlier is actually supposed not to be part of the data, let's say. Suppose there was a measurement error and so the outlier was just because of the noise. Then you would get better clusters by removing that point. In the class, I don't want to remove them, but you know, in normal life, you might want to remove the outliers. Now, the problem is removing outliers is a costly operation. First of all, think about how do you define outlier. Exactly. Far away from everybody else, okay? So in the space, in the distance space that you are capturing, right, essentially in a delta neighborhood of that particular point, okay, there are less than epsilon other data points. That's how you think of outliers. Okay, and to be able to efficiently catch the outliers, okay, you would need efficient data structures to begin with. There are data structures like R trees, which essentially try to index the data such that the neighborhood of the data points can be easily read off from the data structure. And if you have that, then you can tell who is an outlier, who is not an outlier. But this is a general problem for many clustering algorithms, and it's also a problem for K-means. Okay. The other thing, of course, with the K-means is it assumes that the clusters are spherical, basically, because that's how the tightness will be the lowest if your cluster is nice, tight sphere. Okay. And if you don't have spherical clusters, if you have basically big chains, one chain followed by another chain, then K-means can essentially not have a good guidance as to what is the best way to make up the clusters. Okay. So those are all the problems with K-means. The advantage of K-means is it's a very fast algorithm, in essence, because it's basically linear in all the relevant factors. So if you are computing the distance between two instances, let's assume the distance computation is order m, let's assume, which is the dimensionality of the data point. Okay, then reassigning clusters would require kn distance computations. K is the number of clusters, n is the number of points. So each point has to compute its distance to centroids and then decide. Okay, so there's kn distance computations. Each distance computation is OM, so k and m. Okay, and computing the centroids is again ONM, and assuming these steps are done once for each iteration, you will get, for each iteration, it's k and m, and the number of iteration is I, so I k and m, or L k and m. Okay, so that's basically what K-means does for you. It is linear in the number of iterations, linear in the number of data points, linear in the number of clusters. It's a good algorithm. In a minute we'll see hierarchical agglomerative clustering, which is a square algorithm. So it's quadratic in the number of data. Okay, so you can. So the reason people like K-means is it's fast, but it gets you to. It requires K to be given upfront, and it also goes to suboptimal. Yes.
I was just wondering, is there a maximum number of iterations that it can reach?
That's a good good question. There are results on that, but I'm not talking about it. Okay, so that's K-means. Okay, what I'm going to talk about next, K-means is sort of a flat clustering. Okay, so what we'll discuss now is a different type of algorithms called hierarchical clustering algorithms. Of them, basically, in essence, you want to generate, instead of saying how many clusters are there are exactly K clusters, you might say, well, essentially, as I was saying last class, if you're trying to cluster within Phoenix metropolitan area, then we will say Tempe cluster, Chandler cluster, and Mesa cluster, etc. And when you are looking at the Arizona level, then maybe you'll say Maricopa County cluster and some other county cluster. And you look at the national level, you'll say the state clusters. So the clusters always have this hierarchical structure. So the question is, can I automatically generate hierarchically structured clusters? The advantage of hierarchical clustering is there's never any question as to how many clusters are there supposed to be. Right? Because I can always cut it any which way and I can get the number of clusters I want. So for example, if here is a hierarchical clustering where at the edge every element is a cluster by itself. Okay, and then essentially by the end here everything is one cluster. If I want two clusters, I go here. That would be, I'm sorry, no, this is one cluster. So if I want two clusters, by this time actually I have this whole thing is one cluster, this whole thing is another cluster. If I want three clusters, then I have this is one cluster, that's one cluster, that's one cluster. So any cut set here will give me the number of clusters I want. Okay, so it sort of removes this question of how many clusters are there supposed to be. It's a multi-resolution cluster. Okay, the way you can generate something like this is you can start bottom with individuals and start merging them. If you do that, then you're kind of agglomerating things into bigger and bigger clusters. So that's called hierarchical agglomerative clustering. I'll talk about that in a minute. Okay? A different idea is assume that everybody is one big cluster. And then start saying, let's assume I want to split this cluster into two clusters. What would be the best two clusters I can find? And then I can take each of these clusters and split them into two clusters again. What's the best two clusters I can find? That would be a divisive hierarchical clustering. Okay? So bisecting K-means is an example of divisive hierarchical clustering. So I'll talk about that first and then we'll talk about hierarchical agglomerative clustering. One is coming down, which is full cluster to many small clusters. The other one starts with many small clusters, becomes one cluster. Okay? Bisecting K-means is first one we'll look at, and the idea is very simple. Essentially, you are going to start with the data and you first split it into two clusters. Okay. Now, since the clusters that you start with are going to then decide how the lower clusters are going to be formed, you want to be serious about the two clusters you get. So what you will do is essentially you're doing K equal to 2 clustering. Except you will do multiple times. You will start with the data with two different seeds, K different pairs of seeds. Not K, sorry. J different pairs of seeds. So the idea is I have a whole bunch of data and I need to cut it into two parts. Okay, so I'll first assume this is one pair of seeds, and I'll do K-means, and you will say this is one cluster, that's the other cluster. Then I'll also do one more pair, another pair, this and this, and I'll get one more cluster. Okay, then I'll do another one, I'll do one more cluster. There are three different two clusterings. And you just compare them in terms of the intra-cluster tightness measure and see whichever is the best, you pick that. And you commit to that. Okay, let's assume the one in red is the best, so then you come into that. At the top level, the set becomes these two clusters. And now, next iteration, you pick one of the existing clusters and do the same thing all over again. So you recursively decompose it. Okay, and it's basically bisecting K-means. Okay, so it actually you can think of it from the K-means direction and see that it removes two of the problems that K-means has. One is it no longer requires what the value of K up front, because it always is just bisecting. Okay, and if you needed 3 clusters, then you can always go to the hierarchy and then pick the top level 3 clusters. Okay. The second thing it is doing well is it's considering multiple pairs of initial seeds each time. Okay. That way it tries to avoid the local minimum problem. So that's the way you can think of it as a variant of K-means, but really it is also a divisive hierarchical clustering, because at the end of it all you get a hierarchy of clusters. And these clusters are decided from top all the way down. So it's a divisive hierarchical cluster. So it's an idea which sort of makes sense both from the K-means side and from the hierarchical side. Okay, so that's one idea. Okay, now yes.
Yeah, when we are bisecting, how many trials we are going to get a best?
You basically pick. The 3 is better than 2. I guess that's about it. So in this example, we are just saying j equal to number of 1 to number of iterations, and that's just an input. Okay, the bigger that is, the more time you're going to take, but you're likely to get better optimal cluster.
One more question. In this approach, if I have to get 3 clusters, so probably I will end up getting non-uniform clusters here.
There is no, that's true, but on the other hand, how do you know there is anything better? It's not, first of all, the word non-uniform cluster makes no sense to me. Okay, what is that supposed to mean? Should clusterings be such that all clusters should be equal sized? I mean, what do you mean by uniform? It's a good question. Think about it. What do you mean by uniform cluster?
Let's consider we have a fonts in a certain.
No, don't give me an example.
Uniform.
Don't give me an example. Okay, so for example, suppose I have my class. Okay, what would be a uniform clustering into grades? Equal number of A's and B's and C's and D's. What is uniform? Are that all of them are equally tight? In which case, this is taken care of. Okay, so the point I'm trying to make is, it is true that if you were to compute 3 clusters this way, so suppose if you were to compute the hierarchical, divisive hierarchical clustering, and you're taking the 3 clusters, then you get this as the 3 clusters. Had you done k equal to 3 on the original data, you may not have gotten this. But who is right? Right? Again, if you are talking about optimal 3, then I can understand. But neither of you are doing optimal 3. Okay? It's a good question. So the other thing I'm going to do is, instead of going divisive, I'll go agglomerative, going from bottom up. It almost looks like I'm wasting time, but it actually is an interesting idea which makes you, until now, you never had to use the idea of the distance between 2 clusters. Remember, we defined distance between 2 clusters. And there are multiple ways of defining distance between 2 clusters. You can talk about 2 clusters are as distant as their closest points, as distant as their farthest points, as distant as their centroids, as distant as their average of their pairwise distances of points. 4 different ways, at least, I can define the cluster distances. I made the whole slide up. Have I used it till now? I've already done, 2 clustering algorithms. I haven't used intercluster distance at all. Because K-means doesn't do intercluster distance, and bisecting K-means also doesn't have to do intercluster distance, because it's using K-means. Okay, when I'm going in the hierarchical agglomerative clustering, on the other hand, I start with individual elements and I start combining them into clusters. Okay, so the interesting question then is that in the beginning, essentially, you are computing the distance between individual data points. But after some iterations, there may be you no longer have data points. You have some sets of data points, some clusters of data points, including singleton clusters. And you need to compute the distance between the clusters.
But
Yes.
you can treat those clusters as a single data point.
Well, the question is, then if you do that, then you have decided to count the cluster distance in terms of centroidal distance.
Yes.
Why is that right?
But why is it wrong?
Well, the point is, again, as I said, there are different, there are different ways of, you will get different types of clusters if you define the cluster distances differently. Okay, so for example, as we'll see in a minute, the single link one tends to get you chain-shaped clusters, whereas the complete link one tends to get a spherical shaped cluster. Okay, but anyway, let's look at that hierarchical clustering. So here I'm actually doing the hierarchical clustering on one-dimensional data, just to make it simple to begin with. Okay, so in this case, and then in this particular case, I'll assume. So I started with 1, 2, 5, 6, and 7. Okay, so the idea would be you assume that you have a set of clusters. In the beginning, you have a set of singleton clusters. Then you compute pairwise distances between all these clusters. Okay, and pick the pair that has the lowest distance, and say you guys should not be in two clusters. You are one cluster. And you make them into a single cluster. Now you have one cluster less. Okay, do it again. Okay, so that's basically what hierarchical agglomerative clustering is. So an example here, you start with 1, 2, 5, 6, and 7, and you look for find two closest objects to merge. And in this case, it's easy enough. Basically, 1 and 2 are very close to each other, 5 and 6 are very close to each other, 6 and 7 are very close to each other. And clearly, 2 and 5 are not too close to each other. Right? So there are at least 3 pairs that are equidistant from each other. They're all at the lowest distance. Okay? You pick, break ties randomly. So let's assume that I just pick 1 and 2 to merge. So then my data points will now be 1, 2 as a cluster and 5, 6, 7. In this example, I have replaced the 1, 2 cluster with the point 1.5. In some sense, if I did that, I'm using centroidal clustering. So I'm assuming that the cluster is determined, the cluster is completely represented by its centroid, like the way you were suggesting. So in this example, I'm doing centroidal clustering. Okay, but I don't have to. I can actually keep both of them around, and then I can do single link and multi link if I want. Okay, so then now I'll actually my data now will be this 1, 2 cluster, 5, 6, and 7. Now I look for any pair of the nearest pair of clusters and merge them again. So in this case, essentially, what did I do? I merged 5, 6. So 1, 2 cluster, 5, 6 cluster, 7 cluster. So that's why 1, 2 cluster, 5, 6 cluster, 7 cluster. Okay. At this point, I have 3. I still want to merge. Okay. And what do I merge? Which will be the closest to? These two will be the closest to. So 5, 6, 7 will be merged. At this point, I only have 2 clusters. I merge both of them. I will get one single cluster. That's how hierarchical agglomerative clustering works. Okay, the thing that this example didn't show, but I've been mentioning in the background, is you are making decisions about closeness of pairs of clusters. In this case, I just went ahead and assumed that a cluster is represented just by its centroid. But we know that that's not required. We can actually use multiple ways of defining clusters, cluster distances, and depending on the way you define the cluster distance, you get a different kind of cluster. And sometimes you might know a little more about the data you're trying to cluster. Okay? And you might know, for example, that the data you're trying to cluster is likely to have chain clusters rather than spherical clusters. In which case, you will go with single link clustering. Single link as the distance between the clusters. If you don't know anything at all, then all of these are, like as you said, all of them are they will come up with different clusterings, but you don't know which is better. Because after all, it's unsupervised learning, you will not know in the end whether or not you are right. If you have a little more information, then you could use that in essence. Okay. For now, what I really want you to understand is that you will get different clusterings if you define cluster distances differently. Okay. And this is that example that I'm going to do here. It's again Euclidean space, assume Euclidean distance. So if I use single link clustering, okay, where the distance between two clusters is equal to the distance between their closest points. Okay? Then what happens? So in the beginning, of course, each of them are individual points. Then when I'm looking for pairs to cluster, I would be, until here, I would be going fine. Because this pair is close, this pair, they're all actually equidistant, and so you pick them in some order in cluster. So I have 4 clusters. Now starts fun. At this point, I actually have to define the distance between this cluster and this cluster. Now, if I'm doing single link, then the distance is this. Okay? For these 2 clusters, the distance is this. For these 2 clusters, the distance is this. For these 2 clusters, the distance is this. So if you're deciding who should this guy be merged with, it cannot be merged. It has to merge with this because the distance with this is lower than with this or with this. Right? So you will make the decision to say that's a cluster and that's a cluster. And then of course when there are only 2 clusters, you combine them, you get one more cluster. So it's, circles is a way of showing the hierarchy too. Right? Okay? So now if using the same exact data, if I was using complete link as the distance between the clusters, then what happens? I come again up to this point. Now remember that the distance between these 2 would be that much. Distance between those 2 would be that much. And distance between those 2 would be that much. Right? Okay? Of those, which one is the lowest? This one. So I would merge with that. Okay? And then merge. So I did everything else the same. The distance measure for between 2 points is the same. It's not that I shifted from Euclidean to cosine theta distance. It's the same exact distance I'm using. Okay? So I'm using the Euclidean distance, but because of the way I defined the distance between the clusters, I get a different clustering. Which is a better clustering? You might know about your, depending on your domain, that one of them is a better cluster. If you don't, then you just pick one. Okay? So that's that point. One last thing is, of course, that you might say the single link and complete link are both seem to be kind of crazy. They're just betting on either the closest 2 points or the farthest 2 points. Why not average distance between clusters? The problem, by the way, much of this actually, you should start thinking about how much computation am I doing and how do I do this efficiently? Because I said, without without showing any particularly, distressed emotion, I said, I'll just compute the pairwise distance between clusters. Every iteration I'm computing pairwise distance between clusters. That's a pretty costly operation. Okay? At least it would not be too hard if in fact the distance computation itself for a pair of clusters is cheap. Now if I go to average distance based, average of pairwise distances between 2 clusters as the distance between those 2 clusters, then even computation of the distance is going to be now proportional to the multiplication of the sizes of the clusters. Because there are n points here, m points here, there are n times m pairs. For each of them I have to compute the distance, I have to add them all up, divided by the number of pairs, I'll get the average distance. So the distance computation itself would be costlier. You see what I'm saying? So that's why, although people like group average distance clustering, they typically don't do it because it's just too costly. However, it turns out that the vector similarity distance that if you're using vector similarity as the distance measure, it has this beautiful property that computing pairwise distances and taking the average is the same as taking the cosine between the two centroids. So that's what this is saying. So what I need is basically the document I coming from C1, document J coming from C2, I need to compute the dot product of Di Dj, right? And then I need to sum over all the pairs and divide it by the number of pairs, which is C1 size and C2 size. That's when I will get the average distance, right? However, this can be written essentially as this, where this is the centroid of the first cluster, and this is the centroid of the second cluster. So here is a situation where it's one of these nice properties of the cosine theta distance. It actually makes it quite cheap to compute group average distance. Okay, so if you are doing cosine theta similarity anyway, then you are better off actually using group average distance. Because in some sense, you are assuming that the idea of making each cluster be represented by its centroid is no different from taking the averages in that case. This only holds for this distance measure. It doesn't hold for any other distance measure. Much of whatever I talked to you till now doesn't depend on the distance measure. You can use Euclidean, you can use cosine theta similarity, you can use the Jacquard similarity. By the way, that also is possible. You can do clustering using Jacquard similarity. Okay, any distance measure can be used. But this distance measure has this special property. So it actually is useful for group averages. Okay? So that's regarding hierarchical. So we started with hierarchical clustering. We talked about divisive hierarchical clustering, which is bisecting K-means. Then we talked about agglomerative hierarchical clustering, which is starting from the bottom and merging. Okay? You do need to merge efficiently. You need to compute pairwise distances efficiently. Okay? And also the clusters you get, the clustering you get, the hierarchies you get would depend on how you define the distance between the clusters. Okay, that's the point he made. Okay, one interesting point, of course, of the hierarchical agglomerative clustering is that first of all it's deterministic. It unlike K-means, which kind of asks you for the initial K seeds, and then the final clustering depends on the seeds you started with. Okay, hierarchical agglomerative clustering, given the distance measure between the clusters, it will come up with the same. If you read on it, it will come up with the same hierarchy. Okay, but it will take n square time because you are computing distances pairwise in the bottom itself for all pairs of individual points, and there are n square points. But n square pairs, rather. There are n points and there are n square pairs. So there itself you know that it takes n square amount of computation. If each distance computation takes unit time, then you take n square amount of computation. Okay, so hierarchical agglomerative clustering has this problem that it takes. It's actually a pretty good idea because, as I said, it doesn't depend on the number of clusters. You don't need to give it K. Sorry, I'm not put that the good property of it is that it doesn't require K, but the bad property is it takes n square time instead of O(n) time. One idea is this idea called, so here's the interesting thing though. K-means required K. And I told you that had you given me the hierarchical clustering, I can get you, the K. Right? Because the hierarchical clustering is telling me, how to split into K equal to 3, K equal to 4, etc. Okay, so one idea is to do hierarchical clustering on a small subset of the data and use that to figure out what is the best seeds for the K-means. Okay, so here I will conveniently take root n, a square root of n data points randomly from the n data points I have. The reason I take square root of n is because it will take square root of n square time to do hierarchical agglomerative clustering, that will be O(n) time. Okay? So I take square root n data points, run the hierarchical agglomerative clustering. So I have this hierarchy. To the extent the samples I pick is representative of the data, then the cluster centroids would be the same for the final, even if you did it at the bigger cluster. Do you understand what I'm saying? So now, if I then ask you, so I do the hierarchical agglomerative for a time, then I can use the results of this act as the initial seeds for the k-means. So if you are doing k equal to 7, let's say, then I look for the 7, I mean, if I look for k equal to 3, then I look for this, and this, and the centroid circles. And use that as the seeds, and then run k-means on the entire data now, not on square root n data. Okay, this idea is called Buckshot algorithm. Now, it's not that clustering is just 8 algorithms, it is 1,000 algorithms. I'm just picking a few and showing them. Okay, and in this case, I'm sharing this mostly because it has this cute property that you're using both ideas, hierarchical agglomerative clustering and k-means together. And one is being used to help with the other. And you don't want to run hierarchical agglomerative clustering on the whole thing because it will take n square time. And you don't want to run k-means, just k-means, because you don't know what is the best initial seeds to start with, even if I know k. So you're sort of using both together. Yes, there's a question.
Isn't it time consuming to find an accurate representation of the data that's n squared size though?
Accurate. So the whole point of sampling of the data is a very interesting question. Now, I mean, you're not doing root n size, square root n size.
Yeah.
But I mean, the interest, I mean, the idea of how to generate random samples is a theoretically deep question. It's not hard in terms of runtime, but it's theoretically deep. Think about this. Every day, CNN is calling 1,000 bozos in US and asking which of the Republican contenders do you like? Right? They only make 1,000 calls. It's not that they make 10 million calls. I mean, they make 1,000 calls. If one of them is to me, I'll put down the phone, so they make 1,001. Okay, but mostly it's not that they're spending a lot of time deciding who to call, but the strategy for picking people is decided upfront, and that has theory. You know, the famous Dewey wins president's race. Remember the one? Some of you, none of you are born, but there was a time when statisticians predicted that Truman will lose and Dewey will win the presidential election. And of course, they still predicted the other day that Bush will lose and Kerry will win, but that's a different story. And so, in fact, people believed in statistics enough, the sampling enough, that the papers, went ahead and published the next day's paper. And so, the famous picture of Truman standing with Dewey wins presidential election, and Truman actually became the president next day morning. Okay. Now, what went wrong? It went wrong. It was basically because they didn't know how to pick the sample correctly in a random way. It requires theory. So, for example, you can't just pick. For example, one of the things at that time, I believe, I don't know whether this is true or not. One of the things would be that they would call people. Let's say, if you call 1,000 people, it turns out you already introduced bias. You are considering people who have phones. In a culture where everybody has a phone, that's fine. In a culture where only rich people have phones, that's already biased. Okay? And so in general, the point is, there is a lot of theory behind how to get the random sample. Once you understand the theory,